So our previous recording got stopped because of the time limit. Wait a second. Can you see me? Yeah, you can see me. So in the meantime, I had the chance to remember that we need to do a special thing for Python, because unlike R, Python is a little pickier. What happens is when we produce the results for these probabilities, we have two classes. It tells us the chance that it will be in class 1 or class 0. So it tells us, it's basically like in the lecture videos where it says, well, you know, the output could be negative or it could be positive. Now, we want only one of those columns, right? We want the probability that our result will be equal to 1, first class. But that means we also have to clean it up a little bit. So what happens is we will say, well, yeah, result 1 is that thing, but how do we finalize our result? It equals result 1, where, sorry, np.where is kind of like if else in R. Result 1 greater than or equal to 0.5. And what do? We say it's 1, else it's 0. And result 2, the same thing. Okay, perfect. Result output training, confusion matrix. Result 2. What did I call my other thing? Oh, I didn't save it. Okay, see, I said I should have saved it. Testing. Before we drop that column. Output testing. Print F1, F2. And this will frequency 2. Now this is all good, but let us go one step further and calculate the accuracy. It had some weird name in Python. Something with a T. Just a second. Okay, so apparently the name of the diagonal, when you sum the diagonal of the matrix, it'll be np trace. Trace. Frequency 1. And we divide this by np sum. Sum. We'll do the same exact thing. Accuracy 2. Please work. Should work. Ah, the suspense. Yay! It worked. Oh, wait, no, it didn't. Sorry about that. What did we get over here? Something's wrong with the matrix. Let's see. Last time this happened, I couldn't figure out what on earth was going on over here until I just deleted the logistic thing And it worked. Because by default, I think it already does it. Yeah, see, now it works. So basically, if you want logistic, you don't tell Python to do it, and it automatically does it. It'll still work if I do something like activation equals 10h. So it will still work. But for logistic, I found that it's better to just like let it choose it by itself. So there we go. Not bad. I mean, 67% is better than 33, right? 33 would be our just random probability if we just had it all done random. So now, or no, that's not true. That's for if we have 3 different classes. If we have 2 classes, it will be 50%. Yeah, that makes sense. So 67%. All right, well, there's my beautiful code. When it comes to error, remember how in R we had like central, so it was CE error function in Python, and it was so easy to change it in R. In Python, though, to change that is quite difficult, so I didn't really do that. Plotting is also relatively messy, but what we can do, another thing that we can do that is quite interesting, we can print the n iterations. We can print also best loss over here. Oops, sorry, best loss. It will tell us. Here's what it will tell us. So it converges after 166 steps, and this loss over here is when the derivative, the partial derivative of the loss function stopped improving substantially, and hence it stopped our algorithm. So in the back propagation. Now what we can do also is we can adjust the number of nodes in our layers. Let's say 3, 4. Or 4, 3, I don't remember what was in the video. Same accuracy. Of course, this all depends, and as you said, it's trial and error. But maybe we invent a better model and it will be even better convergence and all of that. So that is it for the video. We have successfully built and trained our neural network. Yay! See you in the next video where I do the same for the 2009 paper.